Well, so far, looking at different techniques, we have managed to speed up our embedded processors quite a bit. But the question is, can we do more? What about reducing code size? What about reducing data segment size? Is the order in which variables are accessed important? If so, how? Let us see. The program says, I need an access to that variable A now. Then it says, then I need that variable B after this. Then it says, I definitely need that access C at this point. The compiler says, gee, are you done or are you throwing more accesses at me? And the program says, I'm not done. I need that A again. The compiler says, wow, maybe you should have thought through the whole access sequence and presented it to me in one shot. Maybe I can do something good with it. Is that the case? Absolutely. The sequence of accesses is very, very important. Modern embedded processors take advantage of the order of accesses through something called auto-addressing modes, which leads to very interesting compiler problems to be solved, which optimizes not only the code size but also the data segment size. One of the key topics that we are going to focus on in this lesson is the code size and data segment size, how they are important and how modern embedded processors have addressing modes which can be utilized to reduce the code size. And we'll also take a look at certain data segment optimizations which will help us reduce the data segment size. So the problem that we are going to look at is called as offset assignment problem. So let us take a look at what this problem is all about first, and then we'll look at different types of solutions in this lesson. The problem that we have is how to efficiently use what is called as an address register, which is present in many embedded processors. What is this address register? The address register contains the address of some operand that you want to fetch from memory. Now you can generate this particular address by doing base plus offset, or you can keep it using some other means. And what we do is we do a load on this particular address register, and we get a value of that particular location, whatever is contained in that location, which is pointed to by the address register, and store it in register R0. Now, what happens in this particular process is, what is the next location memory that we want to access? If it is right next to the current location, then we can increment the address register as shown over here. Notice that the use of address registers therefore costs two instructions. One is to access it using address register, and the second one is to increment it to go to the next location from where you are going to get the next operand. And these are the instructions that we could generate without a particular support, what is called as auto-increment mode. Now many embedded processors, as I mentioned, have what is called as the auto-increment mode. What is auto-increment mode? The auto-increment mode allows you to do both of these operations in one instruction. In other words, you can do a load from the address register, and you can also increment the address register to point to the next location from where you can get the next operand. And that way you can cut down on the number of instructions from 2 to 1. Now you may think that, oh, what is the main thing here to just cut down by one instruction? Remember, this occurs very repeatedly in embedded processors. Every time you go to memory, you will have to keep manipulating the address register, and you will have to execute those many instructions. So it is almost saving you 50% if you are able to get rid of these address calculation instructions such as AR++. And therefore, the use of auto-increment mode is very important to reduce the code size and also improve the code efficiency. So what are the goals of auto-increment decrement addressing? The goal is to maximize the use of this mode in generating the instructions, and therefore reduce the code size because now you have 50% less instructions, and also increase the execution speed because now you are executing fewer instructions. Now notice that we need to make sure that the next address is right next to us if you are able to use the auto increment mode. So this problem means that how do you arrange these different operands so that you can go from one to the next which is right next to you. Now let us test our understanding of this offset assignment and address register issue by looking at a simple quiz. I'm going to first explain to you what is going on through this simple program, and then we are going to do this simple quiz using the right hand side. So what we have here in the stack is different variables which are arranged such that first is A, second is C, third is B, and fourth is D. And what we have is a simple program which is trying to take advantage of this layout of variables by using this auto increment mode. Let us see how this program does that, and then I'm going to ask you to modify the program on the right hand side to take advantage of this layout again to use the auto increment mode over here. So now let us take a look at the answers here, how we can take advantage of the address calculation code using auto increment decrement. So the first box should be marked as AR++. Let us see why. What we did first here is we loaded the address of A into AR. Then we carried out a load from that address into R0. So we carried out the value of A into R0. And the next thing that we are supposed to access as per this code is C. Now let's see where C lies here. C lies right next to A. So we can take advantage of auto increment here, and that's why we did AR++. Now as you can see here, the address register will automatically point to C so that we don't have to do an explicit load of that address into the address register. Let's take a look at the next one. Now we are at C. We did a store into C's location using R1. But let's now look at what is the next location that we have to access on the stack. After C, we are going to access B. Now the B is right below C, and therefore again we can take advantage of auto increment, and that's why we did AR++ here to point the address register to B after the store is over. So now after this instruction is done, the address register is going to point to B, and that's where we'll carry out the load as shown in the figure. Let's now take a look at the third empty box, what that should be. Now you can see here that we are going to carry out the load from the address register, and the address register in the third instruction is pointing to B. But the next address that we are accessing here is D, and therefore we can do an increment, again auto increment on this address register, so that for the next instruction the address register is automatically pointing to D, and that's why the third instruction is also AR++. And now let's take a look at the last instruction here, which is D, and the address register is already pointing to D for the last instruction. We'll do a load from that and get the value in R3. After that, we do not have any other instruction in the memory to access, and therefore we don't need to do anything for this address register. It will keep pointing to D at this particular point. So you can see that the code over here and the code over here look very different. What do you find as the difference? There is only one explicit address which is loaded in both the cases, but in the code on the left hand side there are explicit addresses additionally which are loaded. One is C and second is D. In this case there isn't any. The right hand side code is much more compact. It has lesser number of instructions, and it is also very fast to execute. Imagine this occurring inside a loop, occurring millions of times. This code will not only be compact, but it will also be fast. Before we go away on the next slide, notice the dependence of the layout on the stack and whether we can take advantage of address register increment decrement or not. The layout has to be right for us to be able to take advantage of the increment or decrement mode, and that's the key point to be noted here. Let's look at the key concepts here. One is called as access sequence and the second is called as access graph. So what is an access sequence? Simply put, It is a sequence in which the memory locations are accessed. So given a code sequence inside a basic block, we can uniquely capture an access sequence for that block. How can we do that? It's very easy. Take a look at this operation here. Z is equal to X op Y. What happens here? The operand 1 is accessed first, which is X. Then the operand 2 is accessed next, which is Y. And then finally, the result is stored in Z. So the access sequence for this simple operation is X followed by Y followed by Z. Now let us define what is an access graph. Access graph has nodes, each one of which is a unique variable. For example, there will be a node associated with X here, there will be a node associated with Y there, and there is a node that will be associated with Z here. And then we have something else. We note the transitions from one variable to the other, and we also note its frequency. So we associate an edge U to V inside an access graph with a weight W of E if you go between the variables U and V, which are next to each other, WE times. So in other words, we are going to either go from U to V or V to U, and the total frequency of such transitions is equal to W of E. Now, having introduced the formal definitions of access sequence and the graph, let us try to build it through a simple example. So again, the same familiar program is here, which is doing a bunch of load stores from different locations on the stack. The locations are for different variables A, C, B, D, and this is the sequence in which the load stores occur from memory operations. Now remember that in between there could be some other operations and so on which are not relevant for us. So we ignore those. We are just focusing on the memory operations which are load stores. And let us say this is the sequence in which they occur inside a basic block. So the first question is, what is the access sequence here? The access sequence, as you can see here, is very easy to find. It is A followed by C followed by B followed by D. And so that is the access sequence because that's the order in which the memory is accessed. Now let us look at the access graph that is formed by this access sequence. How can we find it? First off, we assign a node for each of these variables. So we have one node here for A, another for B, third for C, and fourth for D. And then we have edges. If the access is transitioning between A and C, we have an edge between A and C. Between C and B, we have another edge, which is shown here. And between B and D, we have a third edge. And each one of these transitions occurs once, so the weight of these accesses, the edge weights, are 1, 1, 1. So again, to summarize, what is an access graph? Access graph is undirected weighted graph. Each of the nodes represents a variable, which is in the stack. An edge represents a transition from one variable to the other, and weight represents the frequency of such transitions. The frequency is counted as follows. If, for example, A to C, we are going once, it is counted once. And then if we are again going from C to A, it will also be counted 1. So the total frequency in such case will be 2. So in other words, it doesn't matter which direction we traverse here. The direction is irrelevant, and that's why this is undirected. So the weight is simply total number of transitions from one to the other or from the other to the first one. So now, having introduced the abstractions of access sequence and the graph, let us see what the problem is and what are we trying to maximize here. So the problem is to be able to cover most of this graph that we have in terms of access graph and leave as few edges as possible uncovered. So before we do this, we are going to define a couple of additional concepts here. The weight of the graph is the sum of the edges in the graph. And what we are going to do is pick a subset of these edges so that the graph is covered. What is meant by coverage of a graph? We are going to pick a minimal subset of these which will allow us to keep the graph connected and will not have cycles in that particular graph. That is called as the cover of a graph. So for example, here is a simple graph that I have. Let us try to find out its cover. The cover is giving us the set of edges. For example, we have these different edges here. One kind of cover would be to start from here, go here, then go here, and go here. That way we have covered all 4 nodes, we have connected them, and we do not have any cycles. So in this case, the edge which we do not use is this, and the other set of edges define a cover of a graph. This need not be the only cover of a graph. We could do something else. For different types of graphs, different covers exist, different possibilities of covers exist, and the one which maximizes the weights is the best cover for that graph as far as our problem is concerned. Now let us look at the cost of a cover. So this consists of the sum of the weights which are not in the cover, which are left out. So the cost of the graph, for example, is the total weight of the graph minus the weight of the cover. That tells us which is the total cost of the edges which are not participating in the graph, and that is called as cost of the cover. So in terms of our abstraction here, the cost of an assignment, storage assignment, is equal to the number of adjacent accesses of variables that are not assigned to adjacent locations. And this is an important point here to see that if we have 2 accesses there and there was certain frequency associated with them, which means that we are going to go from this location to that location with that frequency. But somehow if we do not end up putting these right next to each other, then this edge cannot be covered, and so the cost of this cover is the total sum of such accesses which are left out from the graph because of that layout, which is not putting these 2 right next to each other. Having introduced these concepts of access sequence, access graph, what is the cost of a cover, and so on, let us look at it through a simple example. So let us find, first of all, an access graph for this nice simple access sequence in which we have A followed by B followed by C followed by D followed by E followed by F, again it is followed by A, and so on. So as you can see here, first thing that we do is for each one of these variables we have a node associated with them. So we have A, B, C, D, E, F, 6 nodes for these 6 variables here, and then we put an edge between the 2 nodes if they are adjacent in terms of the access. So let's say we go from A to B here, that's why there is an edge here, and there is one transition here from A to B, so that's why the frequency is 1. Similarly, let's pick some other transition here. We have A to D. Let us see how many transitions are there. So we have one transition from A to D here. We have another transition from A to D here. And we have a third transition now which is from D to A. So this is 1. This is second, which is from D to A. And the third one is from A to D. And that's why the total frequency of transitions from A to D is 3. Remember, again, the direction doesn't matter because we just want to make sure that A to D or D to A can be realized if they are right next to each other. It doesn't matter which is coming first, which is coming next, because in one case we can use auto increment, second case we can use auto decrement. In similar way, we will continue and construct this access graph. As you can see here, let's take another one, A through F. How many transitions are there? So you can see that we have F to A, one transition, and we have F to A, another transition, and that's why we have a frequency of 2 here. So in a similar way, we'll build the whole access graph, and then our problem will be to be able to cover this graph by picking the highest cost edges so that we have a cover for this graph. Again, what is a cover? Cover means we should not have cycles, and if we keep those edges which are in the cover on the graph, and remove the others, the graph should remain connected. This particular way of picking the maximal cover of a graph whose sum is maximum amongst different possible covers is called as maximum weighted path cover. Again, what is the problem here that we define? We have an axis graph and we want to pick that cover such that the sum of the edges there is maximum amongst different possible covers. So one cover is going in this particular way, which is what is picked here. Other cover could be just going here, 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 and here. Now, why is this particular cover not picked, which I am showing here, going like this? Let's find out the sum of the weights here. It is 1 plus 1 plus 2, that is 4, plus 2, 6. Whereas the other cover that has been picked here has a sum which is 1 plus 2, 3, 6, 2, 8, plus 1, 9. So this weight of the cover is higher than 6, and that's why this was picked. You can verify that this happens to be the maximum weight path cover here. In other words, if you try finding different covers as I showed here, one of them, and finding their weights and compare it with the weight of this cover, the weight of this cover is higher than that, and that's why this is a maximum weight. Now, what is the cost of this cover? Let's take a look at that. The cost of the cover is the sum of the weights of edges which are not picked. What are the edges which are not picked? This is an edge which is not picked. This is an edge which is not picked. And then this is the edge which is not picked. And similarly, this is the edge which is not picked. So the sum of these edges, the weights, is 1 plus 1 plus 1 plus 1, which is equal to 4. And that's the cost of the cover. So now the next thing to do is, in order to realize this maximum weighted path cover, we'll have to do an arrangement. Now we are going to look at some assumptions by solving what is called as a version of the problem, which is single offset assignment. So we assume that each data object has one word size. A single address register is used for all variables. So that is why it is called as single or simple offset assignment problem. And then there is a one-to-one mapping of the variables to the locations, and we can use auto increment decrement to move the address register whenever we can to cover as much as we can. There is also a different version of the problem which is more realistic. Now in this particular version, instead of having one address register, we have multiple address registers, let's say k of them, from AR0 to ARk-1. And then we have a long access sequence, a set of variables, and the address registers, k of those. In this particular case, what we do is we partition the graph into subgraphs such that each of the costs of the subgraphs for coverage by a particular address register is the minimum. We are going to look at a simple example to better understand this. But again, what is the goal here? We have this complex access graph and we partition it into subgraphs. We give each one of these subgraphs to each one of these address registers, and then we solve the path cover problem independently, and we find the total cost by taking sum of these costs. The total cost should be the minimum one, and we pick that partition which minimizes the total cost as the best partition. A couple of other key assumptions which are involved here is there's a fixed setup cost for each additional register. In other words, we have to load that address register with the initial variable that we want to have it in it. So that's why there's a fixed cost. And then each of the address registers is used to point to a totally disjoint subset of variables. So we just divide the variables, some of them under the supervision of one address register, some others under the supervision of other one, and they are totally disjoint. So that's why we just are able to find the sum of the costs. Now let us look at a GOA, generalized offset assignment example. and see how that changes from simple offset assignment. So initially, again, we have an access sequence here, A, B, C, D, E, A, B, C, D, and all so on. From this, we have derived an access graph, as we pointed it out, which carries the frequency of transitions from A to B and so on. So for example, CD here represents total number of times either we go from C to D or D to C. And that happens to be 5 times here. Let's verify if that is the case here. So this is first transition from D to C. This is the second from C to D. This is the third from C to D. The fourth from C to D. And this is the fifth from D to C. This is 1, 2, 3, 4, and 5. That's why we have a frequency of 5 on this particular edge, which tells us how many times we either go from C to D or from D to C. So in this particular way, we are doing the access graph. And if we run the MWPC problem, maximum weighted path cover problem, to pick the highest cost edges in the path cover, then we get this as a solution. The thick edges that are showed here are the MWPC solution, and the total cost of this solution is the ones which are left out from the solution. You can see that this edge, and this edge are left out, and the cost of this particular solution using SOA is 6. Now this happens to be the case, assuming the whole assignment is done using just one address register. First it may be points here, then it gets auto-incremented, and so on and so forth. But we are using in this particular case only one address register. Under this assumption, the cost is 6. Now what we are going to do is, we are going to take 2 address registers and show you how we can reduce the cost, and that is our GOA problem. So let's say if we have 2 registers, and what we decide to do is keep A, D, and E under one address register, and under the second address register we'll put B and C, and then we'll find out the costs of uncovered edges using the address sequence and find out the total costs. We'll see what that comes out to be. So if we just focus on edges that are concerning A, D, and E, we can remove all the other accesses from the access sequence and build an access sequence which is just focused on these 3. And we can see here the access sequence comes out to be A to D4 and D to E3 and A to E1. And if you happen to do the MWPC on this particular problem, you can see that the solution comes out as these thick edges, and the cost of this is equal to 1. In other words, there will be one access sequence here which will not be able to cover, and if we have one of these edges left out here, then we have to do explicit loads of address register, and that's why the cost is equal to 1. Now continuing the same thing, the remaining variables B and C are now given under the control of another address register, and if we find out the cost of B to C and C to B transitions, which are left out by an uncovered edges, that cost is equal to 0, because we can cover this using address register very simply. It can point here, auto increment takes it here, auto decrement takes it from there back to here. So in other words, there is nothing left uncovered by this, and the cost is 0. Now you may ask me, so if we partition this in one way, and we partition the accesses A, D, and E in other ones, what really is going on? We have taken out all the accesses which have A, D, and E out of this sequence, and we made a new sequence out of that and build a new access graph out of it. We took out B and C, and we built a new access sequence and a new graph of those. That's why those graphs are different than here. And then we also don't need to worry about going from A to B and B to A, because let us look at now the algorithm which is going to do this for us, to do the partitioning of the access sequence, solving individual SOA problems, constructing GOA solutions, and then trying to go from one register to multiple address registers to use them. So this is called as the solve GOA algorithm. Let L be the access sequence of a particular basic block and K be the number of address registers that are available for us. The algorithm works in this particular way. First, it will try to simply solve the SOA, assuming only one register, and the solution is held in H. If the number of address registers that are available to us is equal to 1, then we'll just go ahead and return this solution. Otherwise, what we'll do is, we will try to select a subset of these variables from L. Like in the previous example, for example, we had A, D, and E selected. So such a subset of variables will be selected in P. What we'll do next is, we will build a subsequence of those variables which are in P. Remember again, we took away all the accesses which are not A, D, or E. We just put the A, D, and E accesses next to each other, noted their transition frequencies, and so on, and that is called as the subsequence. We'll build also a subsequence of the remaining accesses which are not in P. And then we will solve each one of these accesses using a SOA, that is using a single address register. We'll try to come up with a solution. The first one is in H1, the second one is in H2. And then we'll compare the costs of such solutions, the cost of H1, the cost of H2, plus setup costs for those many address registers. And we'll compare it whether it is higher than the cost of doing all under one address register. If that cost is higher, then obviously our preferred solution is what? Preferred solution is just to do it using one address register, and that's what we'll return. If that cost is however lower, then H1 is a very good solution, and what we'll try to do is return that, and then we'll try to take the remaining access sequence which is in L2 and see how to cover it by using remaining k-1 registers by again calling this algorithm. So that is why we have a recursive call here. We'll take the first one that is found here, and we'll take the remaining one and try to solve it using k-1 register. It will go back here, repeat this particular process, return it again the next best access sequence for the remaining variables, divide this further, and keep doing this activity until it has tried to use all k registers to cover these different variables. Now you can see here that the key procedure here that is deciding the subsequence is select variables. Which variables should be selected to go together as one access sequence? That's a key step in this. And there are several heuristics which will tell us to select a group of variables together for building a subsequence here. So students, having seen the SOA and GOA as two different types of algorithms, the first one using only a single address register and the second one using multiple address registers, now let us see the performance on some important benchmarks. So first we have results for just the SOA part. As you know, using a single address register, here is the goal to find the best maximum weighted path cover for this graph. I use the word best because really finding the optimal one is an NP-complete problem which we cannot solve unless we do an exponential number of tries. So there are heuristics here for SOA. The first heuristic is a greedy heuristic. What it does, it tries to pick up the most weighted edges and keeps adding that to construct the maximum weighted path cover solution. And then the second one tries to explore multiple edges that are incident, tries to find out how the SOA costs will be, and then it will pick up the best solution at a particular time by adding that edge. And that's why the second approach is called as branch and bound. In other words, it will try to figure out a bunch of alternatives. It will pick the best out of those that are leading to the minimization of cost, and it will include those, and then it will proceed next to the next set of edges to be added. So using these two different heuristics, let us see the performance on a whole bunch of the benchmarks here. We have many different kinds of things here, which are DSP filters. We have some image processing code here. We also have pretty large scale programs here, such as MDSC and so on. So you can see that in general, the branch and bound SOA performs slightly better than the greedy SOA. What we have here is the instruction counts that are generated by both of these algorithms. Again, the goal here is to minimize the code space. And so you can see here that for certain large-scale benchmarks, we have certain savings there from branch and bound algorithm. For example, if you look at this particular dither benchmark, it generates 1658 instructions, the greedy solution, whereas the branch and bound generates a slightly better solution. You can also see that the time it takes to generate the solution also differs substantially. The branch and bound takes 7 seconds almost, and then the greedy one takes only 2 seconds. So the greedy is a fast heuristic, whereas branch and bound is a more sophisticated but slower heuristic. The overall performance you can see between the greedy and the branch and bound, which is circled here, the total number of instructions, is that the branch and bound is slightly better in terms of performance. The number of instructions is less. It is 26,410, whereas for the greedy it is 26,469. The time it takes, however, for the branch and bound is higher. And you can see that we also calculated here what is called as a lower bound in terms of the number of instruction. What is it? It assumes that we had a perfect way of arranging these things on the stack, and so that we could take full advantage of auto increment decrement. If we did that, then we would have 22,091 as solution of the number of instructions, and that is much lower than what is achieved by these. So there is a substantial gap between the best possible solution versus what are achieved here, and we can see that therefore there exists room to improve these techniques even more. Having seen two different techniques, the SOA and GOA, now let us look at what further optimization can be done to in fact reduce the number of instructions. So you can see that the quality of these solutions is really dependent on the access sequence. And the previous solution started with a fixed access sequence, built the access graph, and then had different heuristics on doing the maximum weighted path cover on that particular graph. While these are good ways to generate the data layouts and optimize the storage assignment problem, what that particular approach missed was it assumed a fixed evaluation order. Now in this particular first improvement, we are going to relax the evaluation order. And so how do we do it? We try to transform the access sequence. What are the different things that we use in this particular case? Well, there are many ways to transform the access sequence. What we try to do is first use simple algebraic properties. The first property that we use is commutativity. That is, an expression can be transformed by swapping its operands. That is a standard way of influencing many optimizations in compilers. And we try to apply this to the access sequence problem. And the second one is the associativity. In other words, we'll take an expression tree and we'll rearrange the order in which it's get evaluated, and we'll try to generate different access sequence using the property of associativity. You can easily see that these two optimizations are also used very commonly in other settings in compilers, especially for minimizing register pressures and so on. So students, before we see the effect of algebraic transformations such as commutativity and associativity, let us reinforce a few more concepts in terms of the access sequence generation and the code generation given a stack order through a couple of quizzes, and then we'll see the effect of transformations. So what I'm asking you to do is fill in the access sequence here for this code sequence. So the way it reads is, given this bit of code, determine the order of accesses of the variables. You have the code excerpt on the left hand side with your knowledge of which variable will be accessed and in what order they will be accessed. Please fill in the access sequence in the box on the right hand side. Please go ahead and write your answers now. And so the correct answer is shown in the box, which I'm going to read out. The access sequence corresponding to this code is going to be A followed by B followed by C followed by D followed by E followed by F followed by A followed by D followed by A followed by D followed by A followed by C followed by D followed by F followed by A and finally B. Let us understand how this access sequence comes into being using this code. So again, what is going on is we are going to evaluate the right hand side expression here from left to right. So we are going to have to load first A followed by B and then store the value in C. That is why first three accesses are A followed by B followed by C. And the next one is D followed by E and then store the result in F. And then the next one is A followed by D and then again store the result in A. Finally, we have D followed by A here, store the result in C. And in the end, you do have D followed by F followed by A to load all these variables to evaluate this expression on the right hand side and then store the result in B. Please go ahead and check your answer with regard to this access sequence. And so, having seen the access sequence now, let us see, assuming that this fixed evaluation order, what is the stack layout that we come up with. So from the code excerpt, we generated this access sequence. From there, we generated the access graph, which we are not showing here. But then we ran MWPC on that, maximum weighted path cover, to minimize the cost of uncovered edges. And using that, we came up with this solution of the layout in the stack for this particular access sequence. So again, this assumes that the code is not transformed, it is the way it is, and we can generate the layout using that for the best solution. Now, corresponding to this layout, we are going to do a simple quiz to generate the instructions to test our knowledge of how to take this stack layout and generate code from it. So what I'm asking you to do is convert this particular code that is seen here and the stack layout seen here into the code. What you're supposed to do is use load for loading a value, store for storing a value, add for adding a value, and LDAR to load the initial address. That is to load the address register with the initial address, you use LDAR. ADAR to load relative addresses, that is to add the offsets to make the address register go to a particular location. And SBAR to retrieve the relative addresses again to subtract and go to a different location using the offset. So what we have done is we have shown you some sample code that is generated, solving it initially, and then we are going to ask you to fill it up for the remainder of this access sequence. So let us first understand this code that is generated so that it will help us to take this quiz. First and foremost, as you can see here, we need to access this A, and therefore what we do is we generate the LDAR instruction which loads the address of A into the address registers AR0. Next, we carry out a load on that address register which will bring the value of A in the memory into a register. Now the next thing that we need to do is access B. Now where are we and where we need to go, that is what we need to pay attention to. So our address register is pointing to A, but we need to access now B. So we need to take this address register and make it point to B. And for that matter, we first calculate the number of locations that we need to increment this address register by. You can see that the number of locations we need to increment it by here is given by 1, 2, and 3. So that is B lies at an offset of 3 with regard to A, and that is why we generated ADAR instruction, which adds 3 to the address register, and now it makes it point to B. So this address register, which was originally pointing to A, now is pointing to B by this particular addition. And once we are pointing to B now, we need to carry out a load instruction and add that value to A. So here we have an add instruction which does both for us. It will access the value which is currently pointed to by AR0, which happens to be B, brings it in and adds it to the current value which is in the register, which is A, and that's why we have the add instruction. So far so good. We have done A plus B, and now we need to store this value into C. So what do we need to do for that? We need to decrement this address register to make it point to C, and that is why you will see here something called as post decrement. So after doing the addition, the address register is decremented. Now it points to C here instead of pointing to B. And when it points to C there, we carry out a store on it, which will effectively store the value of A plus B into C here, and this is that store instruction. After carrying out the store, putting the value into C, let us see what we need to access next, and that value happens to be D. Now you can see that the value D lies just one location below C, and that is why after doing the store, we carry out another decrement here to get that register now point to D. So after that store and after doing the decrement, now the address register points to this D. Now what we need to do as per the code here is to get the value of D into a register, so we carry out a load from that address register. So here at this particular point, we have pulled out a value from address register D here after doing this load. And now the next location that we need to access is E. As per the code sequence, the next location is E. Now we are currently at D and we need to go to E. How many locations we need to decrement this register by? 1, 2, and 3. And that's how we generate this SBR instruction, which decrements the address register by 3. And now the address register will point to E. Now after this, we are going to get the value of E and then do an addition to the original value. That's why we have an add instruction here, and it will do the addition of. Now let's take a look at the answers. I'm going to walk you through a few initial answers and let you verify the rest by following the same procedure. So at this last point that we saw, after doing the increment from E, we went to F. So the address register is pointing to here. And you can see as per the code sequence, now we had to do a store. So that's why we generated a store instruction here, which stored the result into F. And after F, now you can see that we need to, as per the code sequence, from F we need to go to A. So what we need to do is do an increment, and that's why this instruction that we generated here is store star AR0 plus, which will do a increment. The address register pointer will point to A. Now at this particular point, we need to do a load to get the value of A in, and we need to go to the next location, which is D, and therefore we do have a load and an increment which will now point to D. The next thing that we need to do is we need to get the value of D as per this and do an addition. That's why the next instruction is add, and it will simply get the value from wherever the pointer is, that is from the D's location, and do an addition. After doing the load of D here, what we do is we decrement the pointer, making it point to A now, and then we get the value from that location and we do an addition, which is D plus A. So now you can see at this particular point, the pointer is pointing to A. We have the addition done, D plus A. But the next thing that we need to do is store this value in C. Now where is C? C is 2 locations incremented in terms of A. So that is why now we have ADAR, which is incrementing the address register by 2. And after this, now the address register is pointing to C. At this particular location, we can go ahead and do the store to put the value into C. And now we are ready here for doing the next thing, which is to generate the next sequence here, which is coming from DFAB. This is the last one, and we will go through the same process. After we did the store, we will start generating. We'll decrement it, we'll go to D, we'll get the value of D here. Then from D we have to go to F. So that's why we have a SBAR to decrement it by 2. We'll do an add here, which is D plus F. Then from F we need to go to A. So we'll do an increment. We'll do another add there, which is at F. But after we do the addition of A, we are going to go 1, 2, 3. That's why we are doing ADAR by 3. Then finally we do a store here. So it's a fairly complex sequence here, but if you follow the logic here and keep track of where you are and add either increment or decrement, or if it is more than one, then use ADAR or SBAR, you will get the sequence here which is shown, which implements this whole code. Before we proceed, let us test our knowledge of building the access graph from the access sequence. We saw in the previous quiz how to generate the instructions. Now let us make sure we understand also how to build the access graph from the access sequence by a simple quiz here. What I have here is again the same code segment, and I have given here an access sequence that is generated out of it. What we have done here for you is also given you a very simple partial graph which kind of shows the connectivity of different nodes here, but we have left out which node is which one, and we also left out the edge frequencies. So using your knowledge of how the access graph is constructed, please go ahead and fill in these boxes with the variable names for these nodes and with the frequencies for the edges. Please go ahead and write your answers now. Now let us start discussing the solution here. So the first node that is getting accessed here is A, and that's what we have here as the first label. The second node which is getting accessed here is B, and that's why we have this node label as B here. Now let us see which is the third node in the access sequence, that is C. Similarly, following the access sequence further, the fourth node that is accessed is D. We fill that in, and then after D, E is here, which is already there. And finally, after E, we get F. So we have this access sequence here for F. After F, we do have A, and that's why we have an edge here between the two. And after A, we have D. That is why we have an edge now between A to D. From D to A, again, we do have a transition, but that's covered by this edge. From D, we go to A, and from A, we go to C. So we do have an edge between A and C here to be added. And then continuing in a similar way, we do have an edge to be added here between D to F. That's why we got this edge. So at this point, we have added all the edges, all the nodes are present. All that is remaining here is to put the frequencies here. Let us see how we go about that. Now to find the edge frequencies, let us start with the transition from A to B or B to A, which is the same thing, and find out the total number of transitions that are there. So if you go to the access sequence, you can see that we transit from A to B here once. And if we keep scanning further, we do have another transition going from A to B here. That is why the frequency of these transitions is equal to 2. Let us continue the process for finding out the frequency of this B to C edge. So if we again go to the access sequence, we go from B to C once, and that's about it. We don't ever again go from B to C or C to B, as a matter of fact, and therefore the frequency is equal to 1. Now let us continue the process for A to C. Let us see how many transitions we have. Here you can see that we have one transition from A to C, and we don't have any other one either from A to C or C to A, and that's why the frequency is equal to 1. I'm going to continue this process and find something for you, and then I will show you the complete solution just in a minute. So A to D, we have to find out how many transitions we have. Again, we'll count A to D or D to A and count their frequencies. So if you scan the access sequence here, we do have first transition A to D, the second one is from DA to A, third one is from A to D again, and the fourth one is from D to A here, and that's why we have total of 4 transitions, and that's why the edge frequency here is equal to 4. So if you continue the whole process, you can see that each one of these edges is labeled with their frequencies, and this is the final solution that you should get. Please go ahead and check your answers now with regard to this is the access graph that we get for this access sequence. Now let us turn our attention to the topic we were at. How does the access sequence get affected because of algebraic transformations? We can make a change to the access sequence, and that leads to better access sequences. So we are going to look at 2 transformations here. One is commutative transformation on expression trees, and what we have for that matter is an expression tree which looks like this originally. The left hand side is x, the right hand side is y, and we have x plus y that is being generated by this tree. Note the order here, x is followed by y. And what we can do is we can use the commutativity property and flip this expression tree so that now y becomes the left hand side operand, x becomes the right hand side operand, and then now we have a different access sequence which is y followed by x, which is doing the addition of y plus x. Remember, x plus y is equal to y plus x, but the access sequence here is x followed by y, and the access sequence here is y followed by x. Now, the second transformation that we have here is associative transformation, and for this we use the associative property which is for this particular tree. What is going on is in this particular tree, y is being added to z first, and then x is being added. So the access sequence for this tree is y followed by z followed by x. But what we did here was we flipped the order of evaluation here. So instead of doing y plus z as the first addition, we decided to do x plus y as the first addition and then do a addition to z here, and therefore the access sequence here is x followed by y followed by z. So again you can see the result of both of the expressions is the same. However, the access sequences are changed quite significantly. So in short, the associativity allows us to do a change of the access sequence. Now let us see how the access sequences change for a code excerpt based on these transformations. So what we have here is the original sequence of doing the operations without any transformations. And here is the access sequence that corresponds to it that we have seen earlier. It is generated by doing A followed by B and then storing the value in C. That's why it is A, B, C here. Then D, E, F, and then A, D, A, D, A, C, and so on. Note here that we were adding A plus B and then D plus E and so on in that particular order. But now look at the order that has changed now. Earlier we were adding A to B. Now we are adding B to A. So we have done commutative transform here. We have changed the expression from A plus B to B plus A using the commutativity property, and because of which the access sequence now is we have B followed by A. Similarly, we have changed the second expression from D plus E to E plus D. So the next thing that we have here is after C is accessed, then we have E accessed first, then D is accessed next, and then F is accessed. And if you continue in the same fashion and each of these expressions have been changed with regard to this, now the way of evaluating these expressions. Because of the transformation, the access sequence has changed here, and this is the new access sequence which is quite different than the original one. So in other words, you can see that the commutativity and associativity do affect the access sequence because the order in which the operations are done is different. Now I'm going to ask you to verify how the code generated is also different because of different access sequence. Again, what we have done is because of the transformation in which the expressions are evaluated, the access sequence has changed. So this is the new code, this is the new access sequence. With regard to that, we have rerun maximum weighted path cover and came up with a data layout which looks like this. And with regard to this layout, and using this access sequence, I would like you to fill it up on the right hand side, the instructions that are generated. Again, we have given you initial instructions that are generated and asking you to fill in the rest here. Let's walk through it very quickly to understand what is given, and then I'm going to ask you to fill it up, the ones which are in these boxes. First, we are going to need to access B, so we are going to load the address into AR0. Then we are going to do the AR0 access. Next, we need to go from B to A here. Here is where B is. The next access is A, which is over here. And so we need to do an addition here, 1, 2, 3. That's why we added the offset of 3 using the instruction ADAR. Now we are pointing to A. We are going to do the addition here using the address register, getting the value of A. So we are done at this particular point with B plus A. And then we need to go to this location C, and that's why we did an increment here. Then we did a store at this C. And then from C we need to go to E, and that's why we did another increment here. We are pointing to E now, and we are getting the value of E using the load here. Next, we need to go from E to D, because that is the next access here, and we need to subtract 3 locations, 1, 2, and 3, and that's why we have SBAR 3 here, and that's when it will point to this D. So at this particular point, having shown you what is going on here, I ask you to come up with the remaining instructions manipulating the address register pointer. Again, I ask you to use LDAR, SBAR, and increment or decrement to manipulate the address register pointer. So with this knowledge, go ahead and fill in your answers now in these boxes. And here is the solution now for all these instructions, and those are filled in into these boxes. They are based on this access sequence and the stack layout for the remaining instructions here. Please go ahead and verify your answers now. Again, the way to look at it is to keep track of address pointers and then manipulate it using pluses or minuses or ADAR and SBR instructions, and to make sure that it is pointing to the next address which is needed here. Please go ahead and verify your answers now. We having done it earlier for an earlier example, I won't repeat it here. Last but not the least, we want to see how the access graph in fact is affected by the modified access sequence. So what we have is a simple quiz to help you understand it. We have a modified code segment here in which we have done this commutativity transformation. Based on that, we have a new access sequence here. Using the new access sequence, I would like you to regenerate the new access graph with the right frequencies as shown on the right hand side. So please again fill in the node labels and the edge frequencies. Go ahead and write your answers now. So this is the final access sequence and access graph, and it shows you that this access graph now has become much different than the access graph that we originally had because of the transformation, and the solution has also become different. You can see that this has much lesser number of edges than the previous graph. Now the previous examples showed us that doing the commutativity transformation allowed us to reduce the cost. So now we are going to look at a certain framework which will allow us to do this systematically. So we are going to introduce some definitions here. Let SOAS represent the cost of the optimal simple offset assignment solution for an access sequence S. Given a set of algebraic laws, the least cost access sequence is therefore defined by S dash, which is one of the S's, such that the SOA cost of S dash is less than or equal to S for all S which are modified versions of S with regard to algebra psi. So let us understand this, what is going on here. So original access sequence, the best of original access sequence is S. What we have done is we have applied algebra psi on it, and we have generated a new access sequence S dash. Now again, we using MWPC, we find its best cost. If that happens to be lesser than S for all different S's that we are going to find by using this particular algebra, then that is the least call access sequence, because we can't better that by an algebraic transformation, and that is what we call as least cost access sequence. In other words, what we do is we start with the original program, find its access sequence here, find its cost using MWPC. The optimal MWPC is what we use here, which gives the least cost. Then we do an algebraic transformation, and we keep applying these transformations and finding out new access sequence which are equivalent under commutativity or associativity, and keep finding their costs, and if those costs happen to be lesser or equal, the ones which gives the least such cost is what we call as least cost access sequence. So having introduced this least cost access sequence now, let us see how we can actually systematically find the LCAS. So first, we focus on distinct access transitions. So what is a distinct access transition? The distinct access transition corresponds to a new edge that is being added in the access graph. So for example, we had transition already from a variable A to variable D, but by using a new access sequence, we are being forced now to add another transition from A going to C. So this newly added transition is called as a distinct transition here, which corresponds to different edges. So our goal is to increase the number of consecutive accesses to a variable to reduce the number of distinct transitions. So in other words, we want to go from A to D and then back to A, rather than trying to go from A to D to C and then to A, which will add all these different edges. If we keep shuttling between these A and D and then go to C, we'll have only 2 edges. Otherwise, if we go from A to D, D to C, then C to A, we'll have 3 edges. So that is why we want to reduce the number of distinct transitions. That is our premier goal here. So by reducing the number of distinct transitions, what we are doing is we are not adding new edges to the graph. What we are also doing is increasing occurrences of identical access transitions, such that existing edges are becoming more frequent. And by doing so, we are increasing the weights of covered edges, such as in this particular sequence, we are covering a particular D to B and B to D transition in a significant way, and that's why the MWPC solution will now be better. And that leads to our strategy. We do these transformations, and what we do first is to build candidate access sequences, and then we prune them by retaining those with minimum number of edges or maximum frequencies and minimum number of distinct transitions. So the pruning keeps those sequences which have least number of distinct transitions and highest number of edge weights. On such a graph, if we run MWPC, we are definitely going to get a better solution. Let's now first make sure that we understand the relationship between the access sequence and the access graph, and you are able to fill up the frequencies in the access graph from the access sequence. So what we have here is a quiz. What we have is a small excerpt of code here from which we have derived the access sequence, and from that access sequence we are going to ask you to fill up the access graph frequencies as shown. In fact, we have gone ahead and generated the access graph for you. All you need to do is fill in these boxes with the frequencies and fill in these other boxes with the nodes of the access graph. So for example, we are over here and we'll give you a t off point, which is the access node A, which is corresponding to the variable A, and we have an access frequency of 2 here. So obviously it's like solving a puzzle. You need to put something here to make sure that this edge gets the right access frequency. So using this information of the access sequence on the left hand side and the queue that is given to you and the initial starting point, go ahead and fill up the different nodes here and their frequencies of the edges of the access sequence. Please go ahead and mark your answers now. Let's now take a look at the answer to the quiz 1 in terms of how do we see the access graph here in terms of the nodes and the access edges frequencies. So here is the right answer. As you can see, we'll start off here, and I'm going to explain this particular answer to you. We have the access node here, A, and the access frequency of 2 is given to you. So the second node that we are going to have neighboring A is going to be B, because if you analyze this access sequence, you'll see that in terms of the frequency of 2, the only node that has the frequency of 2 with regard to node A is going to be node B. So that fixes this to be node B. And once we fix that, then what we can do is we can analyze what is the next node that is going to be next to B. From B, therefore, we analyze the frequency of what is the neighbor of B and its frequency, and B and C are going to be next to each other in the access sequence if you analyze this. And the transitions from B to C or C to B, total number of those are going to be 2, so we label this edge as 2. In a similar way, we'll keep filling the rest of the access sequence over here. From B, we'll again analyze another node which is going to be next to it in terms of the access frequency, and we'll mark its access frequency there, and that's how we get this whole answer. So please make sure you analyze the access sequence, find out which node is going to go next to which one, and then fill in the frequencies in these boxes over here. Now what we have done here is we have done some transformations to the access sequence that we presented you in the last quiz, and due to those transformations to the access sequence, we have a new access sequence here, and correspondingly we have a new graph. Look how simple this graph looks to you than the previous one in the quiz 1. And the aim of this particular transformation is to simplify the topology of the graph so that the graph becomes as simple as this. And then to generate the maximal cost access sequence, we just drop the minimum cost edge out of this. So now what we are going to ask you to do is, given this transformed access sequence, again, let's do the same exercise on this graph in terms of how this access sequence corresponds to that graph. And so what we want you to do here is to first fill in these boxes here with the node names which corresponds to the variables in the access sequence, and then do exact same thing, mark the corresponding edges with the frequencies of the transitions. So analyzing the access sequence on this left hand side, please go ahead and mark your answers in the access graph on the right hand side. Now let us take a look at the answers to this new access sequence that we have and the new access graph that we get from it. Here is the answer corresponding to the access graph, and as you can see here, voila, by transforming the access sequence we have a much simpler graph. And if you also note, the frequencies of individual edges here are significantly higher than the previous access graph. And how do we generate the maximum weighted path cover out of this? Well, we have a choice of either one of these edges to be dropped. Either FE could be dropped, or ED could be dropped, or CD could be dropped, or BC could be dropped. These are all the lowest cost edges over here, and dropping either one of them will give us the maximum weighted path cover to this particular problem. And so we have managed to come up with a better solution here because we have transformed the graph to a simpler form, and we are able to solve this graph in a better manner to get the MWPC. And so before we proceed to the next concept, I want to make sure we understand it, what kind of transformation we did here. So let's focus on this instruction, number 3 and number 4. And we have interchange A and B here and use the commutative property here. And we have interchange E and F here, again using the commutative property here. And with these changes, doing A is equal to A plus B and D is equal to F plus E, doing this transformation, we have managed to get this access sequence over here. And by doing this algebraic transformation, we have simplified the access sequence and also the graph. The previous two quizzes clearly show us the importance of algebraic transformations, how it helps to get the access graph simplified so that we can come up with a better solution for MWPC and therefore lower costs for the generated code. Now, how do we do this systematically? Well, we had looked at a previous algorithm in which we want to do these transformations on the fly, generate different access sequences, and prune the space of different access sequences by keeping only the minimum cost ones. So here we go. We are going to do a detailed example of how this really works through an algorithm and through applying this algorithm to this example. So the key goal here is to prune the different access sequences that we could generate by doing algebraic transformations on this simple piece of code. Remember the two kinds of transformations that we have in mind. One of them is commutative transformation, which interchanges the positions of the operands. And the second one is the associative one, in which we also do this not just for two operands, but for three operands by switching their positions. So for example, for the last one, we could start by doing A first, then F, and then D. So we could associate the expression in a different way, starting with A to F and then resulting expression to D. So let us look at this example and work through it to see how different access sequences are possible, what access graphs they lead to, and how those access graphs could be pruned to keep only the minimum cost or the lowest cost access sequences what we introduced earlier. So let us do this pruning example first, selecting and focusing only on the statement 1, which is C is equal to A plus B. So the access sequence that is generated on the example as is A followed by B followed by C, or A, B, C. If we swap, however, A and B doing a commutative transformation, then the access sequence will be B followed by A followed by C. So these two access sequences are possible. This is the original one, and the second one is under the commutative transformation. The resulting access graph that we have here is A to B, B to C, as in this particular access sequence, or B to A and then A to C, as in this particular access sequence. Since we are at the very beginning of trying out these transformations and both have the same cost in this particular case, both are retained, none of them is pruned. If it so turned out that during this particular process, if one of the transformations had a lower cost than the other, then only that access sequence will be retained and the other one will be removed. And from that step onwards, we'll be using that access sequence which has the lowest cost and go further and prune some other things for the next set of accesses. So let us continue this example now. Now what we are doing here is we are extending this example not only considering just one statement, but considering the next statement as well. The next statement is F is equal to D plus E. Now let us assume that we had picked one of the two access sequences from the previous steps. In this case, let us assume that we have picked ABC as the access sequence from the previous step. And using that as a basis, let us see how we can develop this now the access graph for the next step. Now for the next step, we could do D followed by E followed by F, or E followed by D followed by F. The first one will be corresponding the way the order is, and the second one will be by using a commutative transform on this particular expression of D plus E. So let us say that we, in this case, first chose to keep the order the same. Then the access sequence will simply extend as C followed by D, and then D followed by E, and finally it will culminate at F, since F will be following E in this particular case. So the access graph that we'll get out of this such a sequence of accesses would be A, B, C, D, E, F, which is corresponding to this. And each edge in this particular case will have frequency of 1. Now let us continue the same example, but we are going to implement here the commutative transform on the second statement here, which is going to be the access E followed by D. And so starting with the earlier access sequence that we had ABC, and then doing the transform for the second statement, wherein E comes first, we get this type of an access graph. Now let us continue this exercise and see if we understand what is the next access sequence that could be possible. We have two possibilities here. First one is ABCEDF and the second one is BACEDF. So given these as starting points, what are the next sequences that are possible from this example? Is the next sequence that is going to be there is DAA, DAC, DAB, or is the next sequence ADA, DAC, DFAB? The answer that is correct is the second sequence, ADA, DAC, DFAB. Let us look at the first one. So far we have covered the first two statements in one of the two sequences here, and we are at the third statement here. So the third statement can lead to A followed by D followed by A, or can lead to D followed by A followed by A. So the first three syllables of this access sequence are in fact correct. It could be D followed by A followed by A. But let's look at the next one now. That could be D followed by A followed by C. That happens to be the case. And then if you go to this particular one, so this is also correct. Let's look at the last one. D followed by A followed by B. Is it correct or not? So for that matter, if we go to D followed by A followed by B, we are leaving out F in this particular case, and that's why this access sequence will be wrong. Whereas if you analyze this one, this is correct, because after these two, the next one could be A followed by D followed by A, that is this, and then we have D followed by A followed by C, that is also correct, and then we have in the end D followed by F followed by A followed by B, which is also correct. So this is the right access sequence. Corresponding to each of these access sequences, we'll have again access graphs, and at the intermediate steps, maybe if one of the access graphs become more expensive than the others, then that is the one which will get eliminated or pruned, and we'll leave the rest intact and use those as starting points to add more access sequences to them. And finally, in this process, we would have pruned out the most expensive access graphs and left only the best cost ones, and that's why it will generate the minimum cost access sequence. So we have worked out for you this example beyond the third step, and we have added some more access sequences, calculated their costs, and kept the minimum cost ones over here. So here are the different access sequences, and here are the pruned access graphs that are being kept. And so if you start working through them, the next access sequence that you get is perhaps adding some other edges here from BAC to EDF, and using that as a basis, we get some other costs here and so on. And then finally, if you keep following this procedure and keeping track of the minimum access cost sequence and using those to build the further access sequences, you'll see that eventually we get two different access sequences, and one of them has a lower cost than the other, which is a cost 2 access sequence shown over here, and that will be a preferred access sequence that we have, and the transformation corresponding to that will be the algebraic transformation we'll undertake, and we'll prune out the rest, and we'll use that as the basis for doing the MWPC. You can see that within these two access sequences also, the topology of this particular graph is simpler than that, and so is the cost. So there seems like a correlation between the topology of the graph and access sequence costs, but it is purely coincidental for this particular example. Please note that in general it is impossible to establish this correlation because the problem is NP complete. In general, for a given access graph, simply by keeping simplest topology, there is no guarantee of finding the best or least cost access sequence. The procedure that needs to be implemented here is at each step, only keep the least cost access sequence to build upon, because using those as the basis, we could do some pruning. The question is there a guarantee even in that sense? And the real answer to that is no, there is no guarantee in that sense either. It's only a heuristic, because if you have a least cost access sequence at a given point, there is no guarantee that at the end you will have the least cost solution. Why? Because again this problem is NP compliant. So finally, here are some results as a benefit of the commutative transformation that we have just seen. Originally, we have these solutions coming without those transformations, and then there are better solutions that are shown here with the commutative transformation. And then we are showing you the gain of the transformations over the original solutions. And you can see in this particular case, the gains are pretty significant, ranging from about 2% sometimes to even as high as 12% on other times, or 13% even for the SOA costs. What it means is we have much lesser number of instructions generated for ADAR to load the address register in this particular case, because we have managed to cover all these edges by generating the MWPC in a better way. And so these show the benefits of commutative and associative transforms to keep track of the minimal cost access sequences at intermediate points and use them to prune the space. Again, this heuristic does not, however, guarantee that the solution is the best possible one under the algebraic reordering. In other words, unless we exhaustively enumerate all possible solutions without pruning, and then at the final step choose the best or the least cost solution, there is no guarantee that we will always get the best cost or least cost solutions. In this particular case, we are doing this by pruning it at intermediate stages, and this does not give guarantee of the least cost solution. What about the performance? Remember, this heuristic is only to reduce the code size, because DSPs have limited amount of instruction memory. So the code should fit in. That was the goal of this heuristic. But the secondary benefit is also in terms of having a faster code, because less number of instructions are being executed. So when we analyze this heuristic against the original proposals for access sequence optimizations on these different DSP benchmarks, what are these? These are DSP stones, a set of benchmarks that typify typical DSP operations such as FIR filters, convolution, dot product, and so on. Using these as benchmarks, we have seen what are the different amounts of speedups there. The speedups range from almost no speedup in some cases to some other cases which are almost 19% speedup. In general, there is a benefit of this optimization because the average speedup is about 7%. Having seen the first technique, which involves purely algebraic transformations to gain access to better and better access graphs and therefore access sequences which have lesser and lesser costs, now we shift gears and we look at a totally different way of simplifying the access graph through a technique what we call as variable coalescence. And the key goal of this technique is to again optimize the access graph, but this time by co-locating two variables in the same memory location. Now, what do we make use of here? We make use of some concepts that we borrow from register allocation here. Recall the concept of web. That is, the memory allocations which have the maximal DU chains corresponding to them, we call those as webs. Now, what we can do is consider two different variables corresponding to two different webs. The question is, can they be allocated in the same memory location? If we can put them in the same memory location, we would have significantly reduced the number of nodes in the access graph. And if we have lesser number of nodes, the intuition here is that we may have a better access sequence. So the question is, when can we co-locate two webs in the same memory locations? For that matter, the webs should not overlap or they should not interfere with each other. In other words, the live ranges of one web and the live ranges of the other web should be completely disjointed. If that is the case, then when one web is done with the use of memory location, we can reallocate it to a second web, and therefore we can simplify the access graph. Remember again the lesser number of variables to lay out on the stack, the easier or the better would be our access sequence, because we could probably create a better layout here. To understand this, let us take a look at a very simple example. Here are some memory references. The first one is for B. This is the definition of B, and this is the last use of B. In between there could be some other uses of B here. And so this is the live range for variable B. Similarly, this is the definition of D, which starts only after the last use of B is over, and this particular definition feeds to different uses of D, and the last use of D is over here. So you can see here that the live range of B and live range of D are disjointed, and therefore they could share the same memory location. And if we carry out their coalescing, that is, if we allocate them in the same memory location, we can get rid of an access sequence from B to D and so on. In other words, the same variable can continue to reside in that location, and it simplifies the access sequence as well and the access graph. This is the technique that we make use of to perform the access sequence optimization for this second technique that we are looking at. So what do we do in this particular case? First, we must do the webs by using the definitions that we have learned for the register allocation. So for example, in this case, B, the variable B, has different live ranges, and we'll first separate those into different webs by using the transitive closures of the DU chains that we learned earlier. So the first chain will lead to the first web going for B1 here, and the second one will go to B2. And that's how we'll separate a given variable into multiple webs. You may ask me why this is important. This is important because it gives us freedom to tackle a part of the web by coalescing it with part of another web, and therefore we want to break down these original things into as fine-grained webs as possible. So the goal of splitting things into the web is that the code generator may coalesce variables at its own freedom. By separating the variables into different webs, it allows more freedom for the code generator to decide on the coalescing of a part of one variable with the part of another variable that forms a given live range. So we first separate the variables into stack variables, then carry out their webs, and then perform the coalescing. We in the last slide saw that we are first going to do the separation of values into the webs, and then we are going to attempt to coalesce different webs belonging to different variables at different points. And here is the outline of different things that will happen in terms of coalescing and separation. For the details of the algorithm and how it works in terms of separation into the webs and in terms of their coalescing to produce the simplified access graph, please refer to the instructor's manual. Here are some highlights which we are going to state in terms of the different analyses that have to happen before we undertake the coalescence. Remember that we are going to put two webs in the same memory location whenever they are disjoint, and that means whenever their last references are done. So in order to find out where the last references are for the respective webs, first we have to do alias analysis. What is alias analysis? Alias analysis is in terms of finding out the variables that might be referenced via pointers. Now, imagine a particular variable being referenced by different names, by different pointers. We cannot coalesce that variable that easily because statically at the compile time analysis, we don't know which pointer is referencing where. So we just leave these variables out in terms of coalescence. We don't put them into any location of any other variable because it will be very dangerous. Because imagine that we assume that they were already done in terms of their last reference, but then suddenly we find a pointer which was pointing to them and was referencing them, and we had already taken away their location, and we would be going to some other variable's location in that particular case because we have given this location to some other variable, and therefore we'll find a wrong value. So in short, it is unsafe to do coalescing for multiply aliased variables, and so we'll just leave them out. So we consider all other variables which are not alias to the pointers, and we determine their live ranges, and then the variables which are disjointed in terms of their live ranges, we want to coalesce them together in the same location. For doing this, we have to work with two graphs. One is the access graph and the second is interference graph. The interference graph shows which are the disjointed webs which can be co-located in the same memory location. And in order to do the coalescing, here is what we do. We pick those webs which have high degree on access graph and which have low degree on interference graph. Why do we do this? Because if we coalesce a web which has a high degree on access graph with another one, we are likely to remove lots of edges from the access graph, simplifying the access graph. And having a low degree on the interference graph allows us lots of choices in terms of which two webs to coalesce. Remember, whatever is not interfering with a given web is a candidate for coalescing with it. And so, therefore, the low degree on the interference graph helps because it allows many more choices than a high degree node on an interference graph which interferes with lots of other webs. And so, as shown in the instructor's manual, the algorithm starts picking up pairs of nodes which could be potentially coalesced, two webs that could be coalesced, and in each step keeps track of the costs in terms of the access graph and tries to reduce this cost as much as possible. Again, refer to the instructor's manual for the details of the algorithm and the paper which is giving all these details. The weights on the access graph can be calculated statically or with the profiling information. So there are two approaches which are given in the paper which allow you to select the right candidates for coalescing. To get a glimpse into the workings of the algorithm and the benefits of coalescing, let us do a simple example. So here is a simple excerpt of a program for which we want to do the better coalescing and better access sequence and the access graph. For this code excerpt, here is the access sequence that is produced. A followed by B followed by C followed by D and so on. You know how to produce this access sequence. And here is the corresponding access graph which is generated for this access sequence which is shown over here. Now corresponding to this access graph, if we do the MWPC on this graph, here is a solution that we get which has a weight of 9 and a cost of 6. In other words, we'll have to insert 6 ADAR instructions in this particular access sequence to load the address register. Now the first thing that we have done on this particular access graph and on this code excerpt is that we have converted this into a web. So here is what we did in terms of doing this as a web by analyzing the ranges and so on, and we have done this conversion for you by renaming certain variables into their counterparts, such as C is renamed into one web C1 and another web C2 and so on. So that is what has happened here. Based on this, we have this new access sequence that is generated and a new access graph. So using your knowledge of MWPC and the access graph, please find the weight of this solution using MWPC on this access graph, and also please find the cost of this and write your answers over here. Please go ahead and write your answers now here. And so if you analyze this particular graph and find out MWPC on it, the weight of the solution is 8 and the cost of the solution is 7. So in other words, we had to add 7 ADAR instructions in this to generate the code. So note that the cost of this access sequence has gone up, but that is only a temporary effect because we have just separated things into web. We haven't done the coalescing on it yet. Now let's take the next quiz on the modified access sequence in which we have done some kind of coalescing. So what we have here is again the same program which is separated into the webs, but in this one we have managed to coalesce certain nodes. In particular, B2 and C2 have been coalesced together into one node. What that means is we are allocating B2 and C2 in the same memory location, and corresponding to that we have this new access graph now. What I would like you to do now is take this new access graph and do a MWPC on it and show me the cost and the weight of the solution that is produced. Again, maximum weighted path cover is what we want to find on this particular graph. So go ahead and find that now and write this as the cost of the solution and the weight of the solution that is produced. Please go ahead and write your answers now. And so if you do this exercise on this particular axis graph and produce MWPC on it, you will see that the weight of the solution is 9 and the cost is 6. So in other words, after performing coalescing, we have managed to reduce the cost back to 6. And what kind of coalescing we did here? We put B2 and C2 together. Now let us complete our knowledge of coalescing through this last quiz. The question is, on the previous axis sequence and the code excerpt that I showed you, was that the only type of coalescing that we could do? The answer is no. We could be very aggressive in terms of coalescing because many webs are disjointed in terms of their live ranges on that particular example. And so what we are doing in this particular case is we are going to aggressively coalesce. So instead of just coalescing B2 and C2, which is what we did in the last example, we are going to coalesce B2, C2, C1, A2 and B1 into one node. And then we are also going to coalesce E and F nodes into one node called Z. So note how aggressive we are in terms of doing our coalescing over here, and because of that, our axis sequence dramatically becomes very, very simple. As you can see here, it is A1 followed by X followed by X followed by D and so on, as it's shown over here, which is what is produced from this after the coalescing is done. And here is the axis graph that we have over here, which is produced, which is very, very simplified in terms of how it looks, both in terms of number of nodes as well as in terms of number of edges. What I would like you to do now for this quiz 3 is to fill in these numbers of the axis graph frequencies, and more importantly, run an MWPC on it and find out the total weight and cost of this particular solution. Why we were able to do these aggressive coalescing? Again, because if you look at the original sequence, all these different webs are disjointed, they do not interfere, so they could be located exactly in the same memory location. So using this information, please go ahead and write your answers to the frequencies here as well as the cost and weight of this solution on MWPC. First, let's take a look at the axis frequencies that we have here, and you can see that how dramatically the axis frequencies are dropped as well on the edges, and certain edges have increased a lot in terms of their axis frequencies because of coalescing. Here is the answer that you see here in the visual, that we have axis frequencies on, for example, edges like X to D as 4 and so on. So this is the answer to the first part. And then if you do MWPC on this simplified axis graph, you will see that the solution is very good in terms of its weight. The weight of the solution has increased to 13, and the cost of the solution, that means the weights of the left out edges, has dropped to 2. So in other words, we have to insert only 2 ADR instructions as far as this new axis graph is concerned. So this example clearly shows the benefit of coalescing, allows dramatic simplification of the costs and the topology of the axis graph, and leads to a very, very good MWPC solution on it. Remember, this strategy relies first on separation of the variables into webs, and then whenever webs don't interfere in the interference graph, they could be coalesced into the same memory location, which is what we use here. Having seen the benefits of coalescing, now let us see how coalescing as an approach works in terms of its novelty, in terms of solving this particular problem. Is it as simple an application, just perform maximal coalescing, or is it something very different? So coalescing, first of all, is not really a brand new technique. Coalescing has been used to eliminate register-to-register moves, as we saw earlier. When two webs are move related, we can just coalesce them and eliminate a register-to-register move. However, that application of coalescing is quite limited. It improves the code, but only removes the register-to-register moves. However, in this particular work, what we are doing is we are applying the coalescing to disjointed webs which are non-interfering and trying to co-locate them into the same memory location. So which is a very different application of coalescing as far as coalescing is concerned. So the natural question that we ask is, why don't we just coalesce a node with everything that it doesn't interfere with and just continue this particular process? So the answer is that maximal coalescing is not necessarily leading to the best storage assignment. Coalescence, in fact, may worsen storage assignment due to the following reasons. When we coalesce two nodes, the coalescence increases the number of neighbors for coalesced nodes. So it kind of degrades the topology of the access graph. Here is how. Our problem is one of finding the path cover. That means in our solution, only 2 neighbors are allowed for MWPC. And if you increase the degree of the nodes, the MWPC has to work much harder to select those 2 nodes because there is a choice of multiple nodes now under coalescence. Now let us strengthen our understanding of coalescing by working through simple quizzes and through examples to see that coalescing is not such a straightforward thing in terms of generating the best access sequence. What we have is an access graph here, and the dark edges shown the MWPC solution for this access graph. The MWPC solution has the node A followed by B followed by C followed by D followed by E followed by G followed by H. Now the first thing that we are going to do on this access graph, which was the original access graph that we had, is to do a coalescing. So we are going to pick here nodes C and H and coalesce those together. And we have given you a topology of the new coalesce graph over here. What I would like you to do is fill in the edge weights here for this coalesce graph in terms of using the original graph for determining these weights. So please go ahead and fill up these boxes here in terms of the weights for the coalesce graph using the original access graph as a starting point. Again, we are going to coalesce nodes C and H here. Please go ahead and fill those boxes now. So if you do this exercise, you will find that suddenly the weights of certain edges which are neighboring to C and H have gone up significantly. This particular weight, CD, has gone to now 5. Some weights remain the same, some have gone up. And here is the modified access graph with regard to the coalescing with different edge weights associated with it. Now we are going to further calculate what is the effect of coalescing on MWPC. By carrying out different types of coalescing, we are going to ask you to do MWPC on them and then tell me the costs that happens as a result of those. So here is the original access graph that we have without any coalescing. We want you to do MWPC on it and find out the weight of this. Write your answer in this particular box corresponding to the MWPC. And then we have the modified graph when we have coalesced C and H together. Again, we do the MWPC on it, and please write the cost of the MWPC and the weight that is generated here. And thirdly, we, instead of having C and H as coalesce, in this particular case we have coalesced D and G together from the original access graph. And with regard to that, again we did the MWPC on it. Please go ahead and write the weight that is found by the MWPC as the profit of this solution. So in these 3 boxes corresponding to these MWPC solutions, please go ahead and write your answers now. So if we go and analyze the MWPCs that were generated on these 3 different graphs, the weight that is associated with the first MWPC is 21, which is corresponding to the edges that are covered by the MWPC. The MWPC is shown here through these red edges and also show this access sequence. And if you calculate by adding all these costs of edges or frequencies of edges, we'll get the total weight here. So now let's do the MWPC on the coalesce node CH and the corresponding access graph. So if you again work through the MWPC, you will see there's dark red edges as being selected, and if you add their frequencies, the total weight that is associated with it is 20. For the last one, the weight of the solution that is produced is 22. For a different type of coalescing, the weight of the solution that is produced has dropped in fact to 20 than the original one, and for the original one the weight is 21. So the first inference is coalescing doesn't always improve the weight. Sometimes the weight can go down, but if the solution is good, the weight will increase and the cost of MWPC will go down. Again, in this particular case, CH is not a good coalescing, but DG is a better coalescing. So in other words, there are different choices of coalescing. Some of them are good, some of them may not be good. And what we are going to have to do is to pick the right choice at each step of the algorithm. Now another thing to note here is that coalescence does not change or gets rid of the costs in the graph or edge frequencies in the graph. It merely reassigns them from certain edges to the other edges, and thereby producing a better solution in terms of weight. We are also reducing the costs here of the solution or the number of ADARs. You can verify this by trying to find out the cost of uncovered or left out edges for each one of the MWPCs. Those which are not covered by the path cover are the costs of the edges here. So find out the cost for this, and for this, and you will verify that the cost of left out edges is the least as far as the last coalescence is concerned. So DG allows us to increase the weight of the covered edges and drops the costs of left out edges. And so the last one is the best solution that is found here because it has the least cost amongst these three solutions. So again, what are the different trade-offs that are involved in coalescence? Coalescence leads to high degrees for nodes in access graph, whereas the path cover wants only two neighbors. And so if we manage to carry out the coalescence so that the degree stays around 2 and doesn't increase too much, we would achieve a very good solution, which is at the heart of the algorithm. For the details of the algorithm, please refer to the instructor's manual. Please read the algorithm in details as given in the paper that is given in the instructor's manual. Here are some important steps that we are going to cover here. So the first part of the algorithm builds the access graph and the interference graph. Then it applies what we call as pre-iteration coalescence, some kind of pre-processing to be done on this access graph to reduce its topology. We then go and run MWPC on this reduced graph. Then we experiment with different ways of doing the coalescence. Again, remember there are lots and lots of candidates for a given web to be coalesced with some other web. Whatever it doesn't interfere with is a candidate, and so therefore we can try different ways of coalescing different webs. At each step, we find the MWPC solution and reject the solution if it has a higher cost than the best solution that we have so far. Finally, we perform program transformations, reorder the statements and the associative and commutative transforms. After this step, the variables are renamed as per their new home locations, memory locations, and the instructions are rewritten too to access the variables from those locations. And now the code is ready for generation using SOA. Wherever there are uncovered edges here in the access graph, we'll have to insert ADARs there, and then we are ready with the code. So the previous slide shows a sketch of the framework that we have implemented in the compiler, and we would like to go over now some critical parts of it. The first part is pre-iteration rules. So the motivation here is, before we actually carry out the coalescence in an iterative manner through that loop and try to measure it MWPC and so on, we apply these pre-iteration rules, and by applying these, the profitability is always guaranteed. In other words, we always improve the access graph here, readying it for further optimizations. So we have a couple of pre-iteration rules here which always benefit the improvement of the access graph. We coalesce all degree 0 nodes with any other nodes, because that way we can improve the MWPC. And then the second rule that we apply as a pre-processing step here is to coalesce all degree 1 nodes with their neighbors. So here is the motivation behind this. If the corresponding edge is already on the path cover, the SOA cost is not affected by this approach. Otherwise, we actually reduce the SOA cost by the weight of this edge. And finally, we have a rule 3, coalesce all degree 2 nodes with the neighbor having a higher weighted edge connected to it. Here is the motivation. If we connect this particular node to another degree 2 node, which is its neighbor, and that has a associated higher cost edge, then we increase the chances of covering that higher cost edge, thereby improving the MWPC. Let us look at the main SOA algorithm now at a higher level first, and then look at the details. So the goal of this algorithm is to maximize the cost savings by recording the best cost solutions, and then it calls the different ways of doing the coalescing at each stage. It finds out the cost of the solution by doing the MWPC and keeps recording that, and then finally at each stage it returns the best cost AG access graph and the interference graph it finds, and in this particular way it gives us the least cost solution. So here are the details of the first stage. It finds 2 nodes in the interference graph which do not have interference, and they should be connected on the AG, and they have the maximal savings. So if it does have, then it coalesces those 2 nodes and updates AG and IG, record them as the least cost solution, and goes to the next stage. And so here is the initial solution that has been found. In the next step, next looks at the modified AG access graph and finds out if there is a further possibility of doing coalescing. If there is a possibility, then it will try to find that effect of coalescing if there is no interference, and it will check the cost of this particular solution with the original one, and if it is better, then it will record that as the better solution, and it will iterate through this loop till it does not find any further node to coalesce. And finally, once it is done, when it does not have anything more to be coalesced, or its profitability has been already ruled out as bad, that is, the other solution is good, then it simply terminates the algorithm and returns that as the final solution. So in other words, at each stage it is trying out different coalescings, finding out if its cost can be lowered. If it cannot be, then it rejects that solution, tries out something else in terms of coalescing. So when it runs out of all the possibilities, it stops here and returns that as the final access graph and the coalescing. Now let us look at the results for different benchmarks here. We have different benchmarks here from MediaBench, and what we have is the costs that are returned by the solution. The original SOA cost is shown in this blue bar. Then the other costs which are shown in the other bars over here after doing the coalescing. And after doing coalescing, only we have certain costs. By doing certain program transformations, we have certain costs, and then we have costs achieved by doing both coalescing and program transformations. So as you can see here, the green bar is the best bar here, that is through coalescing as well as program transformations coupled together, as shown earlier in the algorithm, we are able to reduce the cost the best way. What are the program transformations here? Again, recall that the program transformations involved are commutativity and associativity. Here are the results again for these benchmarks. After doing this optimization in terms of performance, percentage of cycles which are reduced because there are less number of instructions to execute now, and you can see that again the reductions are quite significant for the green bars here in some cases. In others, they are the same. Again, remember the goal of this optimization is to reduce the code size. The performance improvement is a side benefit here. Now remember, another big benefit of coalescing is reduction in the data segment or the memory requirements of the program, and all these variables which are coalesced share the same memory location on the stack. So because of coalescing, there have been dramatic reductions in the data segment requirements for the program. They range and are shown in this particular table. Average improvement is 65%. The other improvements range from about 40% to 75%. So again, major reductions in data segment size apart from the code segment size. The code segment size reductions are due to less number of ADAR instructions. The last benefit that is shown in the paper is in terms of the benefit to GOA. As a result of coalescing, we are able to reduce the access graph so much that now it can be optimally allocated only with very few address registers. For example, only 2 registers are sufficient for optimally allocating it for all these different benchmarks. 3 are sufficient in some other cases, and so on. And so, because of coalescing, we have now a very simple access graph which has huge benefit due to it fitting into the only 2 address registers. What happens to the other address registers? Well, the address registers can hold integral values, so they could be used by the compiler now to allocate register values for program values, not just hold addresses. So that is another benefit, because now only 2 registers are required. The remaining 6 can be used for holding values for the program and not addresses. And so to conclude, here the coalescing along with commutative and associative transforms have major benefit. What do the coalescings yield? They result in dramatic reductions in data segment, excellent reductions in the code sizes, improvements in the performance, and finally we have the best solutions by using only 2 address registers or 3 address registers in some cases, freeing lots of address registers for holding data values and for doing aggressive register allocation. So as a result of this, the code quality significantly improves, and this is one of the major optimizations that is useful for DSP processors. Now remember that the DSP extensions are now commonplace even in ARM and so on, and so it is very possible to apply these kinds of optimizations taking advantage of those extensions. In this lesson, we discovered storage assignment allows us to perform efficient data layouts on the stack, which enables code generation using the auto increment decrement modes. The problem can be solved using a single address register, or we could use multiple address registers. Commutative and associative transforms help modifying the access sequences to simplify the access graph, and that allows better MWPC or maximum weighted path cover solutions for the access graphs. Variable coalescing facilitates elimination of many graph edges and simplification of its topology. This can dramatically improve the MWPC solutions. Variable coalescing minimizes the data segment as well as poses optimal solutions based on just a few address registers, and this was observed for large benchmarks. So what is the takeaway for this lesson? Do not solve NP-complete problems by using complex algorithms. Simplify the graphs by performing transformations, and this is the hallmark of many compiler approaches. For example, interference graph simplification that is based on live range splitting takes advantage of this, and that is the same exact approach which is used in this particular lesson.